Okay, this is a trial run of the talk for the paper here. So making non-Hohmann Mars transfers cheapest refers to the 26-month period where there's just a small window open where you can take a Hohmann transfer, which is lower energy, to Mars than other transfers, and the other transfers are so high in delta V that they're not tenable. You can't. They're too much more expensive. You can't do it. So what I'm going to talk to you about is a different approach that has an effective ISP of 38,213 seconds while still maintaining a reasonable acceleration of 96 millimeters per second squared. We're going to compare that against 380 seconds of ISP, which is the SpaceX expected ISP, and 453 seconds of ISP, which is the SLS expected ISP. So first of all, I want to talk about the Hohmann transfer. And there's always a Hohmann transfer leaving from the orbit of the Earth to Mars. So see here, this is the Hohmann transfer that would leave to get us to Mars. But unfortunately, the Earth is not initially in the correct position. So how can we get, for a future point, there's another correct position, and we want to follow a Hohmann transfer, but how can we skip from where the Earth is now and past where the Earth will be in that future time to where we need to be? And the way we do that is we go from the Earth to some inner orbit, and I've picked an orbit that's 17 kilometers per second in, and that's on the order of Mercury. And then once we're at that orbit, we'll hold steady for a while. The Mercury travels around the Sun once every 88 days, and then we'll come back out from that back to the Earth orbit. And once we're at the Earth orbit at the correct time and place for the Hohmann transfer, we'll just execute a normal Hohmann transfer. So the time that this is going to take is something on the order of 147 days, at worst case 88 days, and 147 days, and then 6 months. So it ends up being an 18 or 19 month transfer, which is longer than a 6-month transfer, but this would allow us to go at any point, at any time, we can go to Mars by following this recipe. So the segments that I've got there, I've got segment A is 17 kilometers towards the Sun from E1. And so here we're going for segment A inward. And then segment B is to synchronize and just holding steady at that orbit. And that's what we're doing here. And then segment C is taking us 17 kilometers per second away from the Sun, which is what happens here. And we end up at H2. And then from H2, we're just executing the normal Hohmann transfer. Okay. So how do we pay for this? It's 80.2 kilometers per second round trip. This is just insane. You cannot do this with rocket fuel. It's just crazy. And the way we're going to do that is we're going to have non-carried reusable reaction mass. So we're going to take a solar sail spacecraft, which I will call a brick. And this can be used as a reaction mass for another spacecraft, which I'm going to call a mothership. And while the mothership is going to execute a non-Hohmann transfer, and the bricks are ejected on using a magnetic train-like ejector at 8 Gs of acceleration for 400 meters of distance, and that gives you a 250 meter per second ejection velocity, which is equal to 900 kilometers per hour. So it's fast. You can imagine a really, really fast train. And that turns out to be 25.5 seconds of ISP. You take the 250 meters per second and divide by 9.8 meters per second squared, and you get your 25.5 seconds of ISP. So we're going to use the, the rockets then pre-navigate to 401 positions that are velocity synchronized, so that as you approach the point, the fuel is waiting for you there. And it's impossible to perfectly synchronize it, so you can imagine maybe you're 1 meter per second not synchronized, and so you have some slight, 1 mile an hour of bumping into the thing, or else you have to use a little bit extra fuel. But this is just to give us an idea of what's possible. So we have 401 of these refueling points, and so the largest distance traveled will be 100 meters per second, or the largest velocity gained will be 100 meters per second. And the mass fraction for 25.5 seconds of ISP over a voyage of 100 meters per second is 1.5. And what that means is that 0.5 kilograms of fuel is required for every 1 kilogram of spaceship. So the round trip, this gives us 200.5 times the mothership mass to Mars and 200.5 times the mothership mass back from Mars for a required round trip of 401 times the dry weight of the mothership worth of bricks, which we're using as our reaction mass. And so because the ejected bricks are still spaceships and they're powered by solar sails, they can pre-navigate to the next location. We haven't lost anything. The fuel is still there. And so then step 3, we're going to notice that we've taken the issue of ISP, which is a physics limit, and we've transferred this into the longevity of the spacecraft, which is an engineering limit. If those spacecraft lasted forever, you could get an infinite amount of meters per second of acceleration using this method. So the effective Earth to Mars segment, the segment D acceleration of the solar sail bricks, is 288 meters per second per month. So this is how quickly we can recover the solar sail brick spacecraft. And so the effective acceleration on segment A and segment C is about 662 meters per second because it's closer to the sun and the photon density is higher closer to the sun. So the cycle time for this setup and resetup of segment A or C is 17. So you have to set up and then once you've cleared it, you have to reset it up for the next transit. So we have to travel 17 kilometers per second times 2, and then we're dividing that by 662 meters per second per month. That gives us 51.35 months to set up the solar sail bricks in order to do this. And the cycle time for segment D is 6.1 kilometers per second times 2 divided by 288 meters per second per month. It gives us 42.36 months. So our total system refresh time is 51.35 months. And with a little bit of time for the docking and refueling and everything, I'm just assuming it's 52 months for a single transit to be all the way back and refreshed, ready for the second transit. Okay, so if we do this now, we can look at the system lifetime. And if we have a system lifetime of 121.33 years, or 69.33 years, this will take a mass fraction of 402, which is the 401 times fuel plus the dry mass of the ship, and it travels either 28 or 16 times the 80.2 kilometers per second for total travel distance, traveled velocity, of 2.245600 million meters per second, or 1.2832 million meters per second. And so if you look at those numbers, I've picked that to give you a system lifetime that will make this system cheaper than the normal Hohmann transfer. So you can now have a lower amount of average fuel consumption using this non-Hohmann transfer that SpaceX or NASA could get with their Hohmann transfer, which is kind of a big deal. So the mass is consumed, no mass is consumed for this entire system. All of your mass is still under your control, and if you were to melt down the bricks and reform it, you'd have to build your computer chips and everything like that. You haven't lost anything, and you could do this all over again. So the acceleration that I'm using here is based on 10% of the mothership being 300 watt per kilogram solar sails, which means you have 30 watts per kilogram. And because we talked about a 100 meter per second segment requiring 0.5 kilograms of bricks, you can find the number of joules by taking 0.5 times velocity squared, which is 250, times the mass, which is 0.5, and so it's essentially 125 squared. And then we can calculate at 30 watts per second, how long does it take to accumulate that number of joules, and that gives you a certain number of seconds, and then you take the 100 meters per second, which was that segment length that you spent all that energy on, and divide it by the number of seconds, and that will give you an acceleration. And that's where we got the 96 millimeters per second squared. And this is remarkable because for a high ISP thrust, having a high acceleration hasn't been done before. Nobody's got a 30,000 second ISP with anywhere near this level of acceleration. And the reason is because this really isn't a 30,000 second ISP. This is a 25.5 second ISP that's being recycled and is not carrying the mass. And that, in that respect, the physics applies to 25.5 seconds. We're throwing things very slowly. It doesn't take very much energy. So energy-wise, we're not constrained on the acceleration. But because we're able to not carry the mass and we're able to recycle the mass, the ISP, or it's kind of like the mileage in a sense, your fuel effectiveness is very good, even though you're not energy limited for your acceleration. No, we are a little bit energy limited, but we're so much less energy limited than other high ISP methods that this is the best high acceleration, high ISP method, except for if you get to things like laser projection, which are theoretically possible but not as practical. Thank you very much for your time.